Yeah, good morning. So we're going to continue the morning. Okay, remember this is we're going to continue from in the last class, in the last videos, we were able to sort problems on thermodynamics, pressure, temperature, work done by a gas, kinetic theory of matter and gas laws, and all of that. So that is that about that. So today I'm going to pick on another topic, light and waves. So we quickly solve the problems on them, explain the theory. Then next we move to electric and magnetic fields. I think that should be the next topic. Then we also have current electricity, where we talk about resistors, voltage, and all of that. In the case of electric and magnetic field, we are talking of magnetic field intensity, electric field intensity, and stuff like that. So we look at them one after the other, for as far as we can go today. All right, now we are starting with light and waves. So we use the questions to actually proceed. Use the questions to have class as usual. So this question says the relationship between wavelength lambda and frequency v and speed of light c in an electromagnetic wave is. So we want to get the relationship between wavelengths, frequency, and speed in an electromagnetic wave. Actually, the relationship is not different from what obtains in other kinds of waves also. So anyhow, it is whatever the wave is, or whatever the kind of wave it is, the relationship is the same. Okay, so we're going to look at it now. So basically, if you talk about waves, we're talking about a disturbance, that travels through a medium, transferring energy from one point to another in the medium without causing any permanent displacement of the particles in the medium. So what do I mean by that? If you imagine this as a water surface, let's say this is the surface of water, just balanced this way. This is some water surface. You have water all below, and then you drop a stone, or you actually disturb, let's say you disturb this end of the stone, of the, let's say, the container. Let's say this is maybe, what can we call this now? Okay, maybe use a bowl, maybe I don't know. Okay, just look at it like you have a big container, like maybe a tank of water. Yes. Then there's a disturbance at this end. It could be a stone dropped at this end, or it could be somebody just shaking the material at this end. So that's what we mean by disturbance. So the disturbance is introduced to this system at this end. But what happens? You are going to see waves. Waves will actually spread out. Okay, from that point of disturbance, you're going to have something like this, spreading out, like that. So that's what we mean by a wave. It is a disturbance that travels through a medium. So in this case, the disturbance travels through the medium and it transfers energy. Yes, sir. Okay, so that's the disturbance. It travels through this medium. I mean, it's just an unsettling. That disturbance, it just unsettles the surface and it travels out like that. And so it is a disturbance. Now the particles of this medium, I mean the water particles that are here, it's not that the water particles here will actually move and they start moving this way. No, it's actually that the water particles here, for instance, a certain particle here will only move to and fro, like it will just go up and down. That's the disturbance. The disturbance always just causes it's just a disturbance of the medium. There's no permanent displacement of the particles of the medium, so the particles just get disturbed. So that's what happens. So that's what I mean by a wave. So to define this very clearly, to be very exact, we usually use this illustration. In the case of this kind of wave, we say that we have something like this. So that's the way the wave travels. In this case, we have the wave traveling this way, like the disturbance starts at this end and it spreads out along this direction. Okay, so um, in this case, or normally in all situations, you can actually describe what happens to the system using this relationship. That is to tell you that what has happened is the particles here are being displaced in this manner. Okay, so you have something like a displacement like this. So at any instance in time, you can have a relationship or a description that looks like this. Okay, so we usually define some parameters based on this observation. Okay, number one is the wavelength of the wave. We talk about the wavelength of the wave, lambda. We talk about the frequency of the wave. We can also talk about the period of the wave. We can talk about the angular frequency or the angular velocity of the wave. Alright, so when you have all these things, what do they actually mean? You know, the same parameters when you discuss them under simple harmonic motion. Okay, because it actually has similar characteristics to simple harmonic motion. Alright, so they mean almost the same thing, or the same thing. You can say the same thing without much error in both cases. So in the case of this, the wavelength is when you have a complete oscillation. That is the distance the wave has traveled in a complete oscillation. That is, in this case, when a particle here has gone to and fro, okay, the wave will have traveled this way. It will have covered this angular displacement. It will have covered this angular displacement also. What do we mean by all of this? You will see that by the time you get to this point, anything after this point is a repetition of what you already have here. So we are going this way. That's exactly what has happened here. So that means from this point to this point, an oscillation is already complete. So from here, it is starting off with another oscillation. That is starting another oscillation from that instance. So a wavelength is the distance it has traveled between this point and this point. That is distance traveled by the wave in a complete oscillation of a given particle of that medium. That is when a certain particle in the medium has gone to and fro. That is, it has left a particular point, it has gone to all available positions and returned to the starting point. That's a complete oscillation. For instance, if this were the surface of the water and this end were disturbed, by the time this one goes, you know, maybe it was originally like this and it goes this way, then returns to where it is, then it has completed a cycle. That's what we mean by complete oscillation. So the length the wave has traveled in that interval is what we call the wavelength. So this is one wavelength. Alright, so when you have a situation like this, if a particle is located at this point and another particle is located at this point, okay, because they have whole number multiples, or they are whole number multiples of a wavelength apart, we say that the particles are in phase. That is, they are exactly in phase. Otherwise we say they are out of phase. What do we mean by in phase? In phase simply means they undergo the same phase of motion, okay, at every instant. That is, at the instant that this was here, this was at the equilibrium position. At the same instance, this was at the equilibrium position. At the instant this will be at the maximum position, this will also be at the maximum position at that same instance. So that's why we say that they are in phase. Alright, so if that was not the case, they would be out of phase. So they could be out of phase by any kind of degree. They could be out of phase by 90 degrees. They could be out of phase by 180 degrees. I guess your lecture did not go into too much details like that. Alright, so that is what wavelength is. In the case of frequency, we are interested in how many oscillations have been made in a second. That is, what is the number of oscillations per unit time. Okay, so of course wavelength, as its name implies, it's a length, so it is usually measured in meter. In the case of frequency is asking you how many oscillations is made in 1 second. So if n oscillations are made, that is by a given particle in the medium, okay, in t seconds, that means our frequency will be equal to, number of oscillations made per unit time. That will be n divided by the t. That is, if n oscillations are made in t seconds, our frequency will be given by this. And of course, this is a number. it is scalar, it has no unit. So this is time, which is in seconds. All right, so we can have this as per second. Okay, that will be the unit of this one. It is per second because this is per unit time. That's per second, whereas this one has no units. All right, so that per second is usually also written as hertz. Okay, hertz, or for short we write it as Hz. So when you see Hz, it is unit of frequency. All right, so I guess that's that about that. And now in the case of period is simply the time taken to complete one oscillation. That is, for instance, the time it will take for this wave to travel from this point to this point, okay, is the period of the wave. Okay, so the period is time taken to complete an oscillation. All right, so that means if the wave completes n oscillations in t seconds, the time taken to complete an oscillation will be the time divided by the number of oscillations completed. All right, so obviously in this case the time will be in second, and this one has no units. Okay, so that means the unit of our period is seconds. Okay, and it is the reverse. If you notice, it is the opposite or the multiplicative inverse of f. So obviously our t is just equal to 1 over f, or you say that f is equal to 1 over t. Okay, anyhow you say it. All right, so that's that about that. And in the case of angular velocity, we are talking about the angular disposition or angular displacement per unit time. So the angular velocity can be given by angular displacement theta per unit time. That is, if the body or a particle in the medium undergoes angular displacement of theta, okay, in a particular time t seconds, then the angular velocity or angular frequency is given by this relationship theta over t. Alright, so what do we mean by theta in this case? It does not appear to make sense here, but the way you look at it is this. If I have a body, for instance, if I have this thing set to this way and it undergoes oscillation, let's say it goes this way, comes to the bottom, then goes back. So I know that it is undergoing some repetitive motion. So at every point in time, I can measure its angle or its angular disposition relative to a particular reference point or reference line. Okay, so that's the idea. So if you have something like let's say this particle is undergoing oscillation. Okay, the oscillation goes to and fro. Okay, at a particular point in time, the body is such that it is on the neutral level. At another point in time, it will be at this level. At another point, it is back here. Okay, so when it is back here, we look at, okay, where is it going next? It is going this way. It is different from when it is here and it is going this way. So between this point and this point, we say that the angular displacement is 180 degrees. Okay, because it is half of a complete oscillation. You know, a complete oscillation is when it returns to this level. So by the time it returns to this level, it has undergone a complete oscillation of 360 degrees. So that's how you measure the angular displacement. Of course, the angular displacement will usually be put in its SI units, which is in radians. Right? So I believe you can convert from degrees to radians. Okay? So from here, for a complete oscillation now, you know that for a complete oscillation, when you have a complete oscillation, you know what theta would be. For a complete oscillation, theta is definitely equal to 360 degrees, and 360 degrees is 2 pi radians. Okay, we just explain that now. And t, the time taken to complete one oscillation, is the period. You can remember that here. Period was defined as the time taken to complete one oscillation. So therefore, for a complete oscillation, we are going to get our omega. Omega is going to be equal to theta, which is 2 pi, all over time, which is t. So we're going to have 2 pi over t. So from here, we're going to have omega is equal to you know, this 1 over t is the same thing as f. That's what we have here. F is equal to 1 over t. So from here, I'm going to say omega is equal to 2 pi f. And that will be the frequency of that. Okay, so the next thing is to talk about the velocity. So this one is linear velocity, not angular velocity. So velocity is total displacement, okay, over the total time taken. All right, so in this case it is total linear displacement, so we can call it x. That is linear displacement of the wave in this direction. Okay, so we can call it x, that this is x, this is y. Okay, so divided by the time, so that will give us the magnitude of the velocity, the linear velocity of the body. So from here we're going to have our, for a complete oscillation, you know, our x is going to be equal to the wavelength, because in a complete oscillation the body or the medium or the particles of the medium will have gone through a length equal to the wavelength. Alright, so from here we can say v is equal to the wavelength, which is lambda, divided by the time. So for a complete oscillation, the time is t, which is the period. Okay, so from here we know that 1 over t again, like we did here, is equal to f. So this is going to give us v is equal to f lambda. So that's the relationship between the velocity of a wave, any kind of wave at all, its frequency, and its wavelength. Alright, so that's the relationship. So in this case, don't forget what each one of them means, so that you don't pick the wrong option in this problem. In this problem, they said the wavelength is lambda. Okay, it's correct, that's what we used. The frequency is v instead, so they didn't use f for frequency, and the speed is c. Alright, so we can substitute all of that into this situation. So in this case, our v is the speed. So in this case, they are telling us the speed is c, the speed of light, is equal to f. So f in this case is v, in the question we are solving. Okay, and wavelength remains lambda. This is lambda. So we have the relationship already. So A says C equals to lambda, not true. B says A is equal to C over V. Lambda is equal to C over V. So obviously that is correct, because if you make lambda the subject here, this is going to be equal to C over V. Okay, so that's quite straightforward. So that is that about that. If you have any further questions, let me know.